Hello, everyone. Tonight, we will embark on a mysterious journey into the depths of space and time. Enjoy listening. Space and time feel like the most familiar things in the world. You don't need a telescope to notice them. You simply live inside them. You wake up in a place. You move through rooms and streets. You look at the sky and you watch moments pass. Space is the where, time is the when. Simple. And then science comes along quietly, patiently, and says, yes, but also not quite. Space is not just an empty box that holds planets and people. Time is not one universal clock that ticks the same everywhere for everyone. When we measure carefully, when we follow light, when we track gravity, when we compare clocks and distances with real experiments, the universe reveals a deeper structure. Space and time are not separate ingredients. They are intertwined. This narration is designed for sleep and relaxation. The goal is not to overwhelm you. It's to gently reshape your intuition, the way your eyes adjust to darkness. You can let the ideas drift by. If a concept feels strange, that's normal. In fact, in physics, strange is often the first sign you're getting close to the truth. Space, in the everyday sense, and why that's not the whole story. In daily life, space seems obvious. It's the room around you. It's the distance between your hand and the cup. It's the gap between buildings. It's the sky above your head. You can point to it. You can move through it. You can measure it with a tape measure. You can draw it on a map. This everyday sense of space is incredibly useful because at human scales, space behaves in a very stable way. It's almost like a reliable stage. You walk forward, you reach the door, you turn left, you arrive at the kitchen. Your brain builds a model of space without you trying, because survival depends on it. For a long time, science agreed with that instinct. In the classical picture, space was treated as a fixed backdrop, an invisible grid that exists whether anything is inside it or not. Objects move through it, but space itself doesn't do anything. It doesn't bend. It doesn't stretch. It doesn't react. That classical view works so well that it can feel like it must be the final answer. It predicts how balls roll, how arrows fly, how bridges hold weight, how planets orbit. It matches the world you see. But physics has a habit of asking a very gentle question with very sharp consequences. How do you know? How do you know a distance? You measure it. With what? With a ruler, a laser, a radar pulse, a calibrated instrument. Those tools are physical. They can move. They can be in gravity. They can be affected by temperature, motion, and environment. So, the story of space is not just space exists. The story is space is what our best measurements reveal it to be. And the moment we begin measuring at extremes, very high speeds, very strong gravity, very large cosmic distances, space stops behaving like a rigid stage. Time, in the everyday sense, and why it becomes mysterious. Time feels even more intimate than space. You can close your eyes and still feel time. You can sit still and time continues. You can't point to time the way you point to a chair, but you experience it in your heartbeat, in your breathing, in the slow shift of attention as you drift towards sleep. In ordinary life, time seems universal. It feels like everyone shares the same now. If you and a friend look at the clock, you expect it to agree. If two things happen at once, they happen at once. End of story. Classical physics supported this intuition. Time was treated as a single steady flow across the entire universe. A master clock, one timeline for everything. But again, physics asks, how do you know time? You measure it with a clock. And what is a clock? Any physical process that repeats reliably the swing of a pendulum, the vibration of quartz, the transition of atoms. A clock is not a magical device outside the universe. A clock is not a magical device outside the universe. A clock is not a magical device. A clock is not a magical device. It is part of the universe. So if clocks are physical, then it becomes possible, at least in principle, that different clocks might not always agree. Not because they're broken, but because the universe itself makes time behave differently depending on motion and gravity. That idea sounds unsettling at first, but there's a calmer way to hold it. Time is not an abstract river flowing out there. Time is something that happens along your path through the universe. Your time is tied to your journey. The moment light enters the conversation, the rules change. If you want to understand why modern physics had to rethink space and time, the key character in the story is light. Light is not just illumination. Light is information. It is how the universe tells you what is happening elsewhere. When you look at a star, you are receiving a message. When you see a friend wave, you are receiving a signal. When a telescope records a distant galaxy, it is collecting ancient light that has traveled for an astonishing length of time. Scientists learned that light in empty space travels at a specific, fixed speed. And here's the strange part. Experiments showed that this speed does not behave like ordinary speeds. Normally, speeds depend on relative motion. If you run towards something, you meet it sooner. If you run away, you meet it later. If you throw a ball from a moving car, people standing on the roadside measure a different speed than the person inside the car. So people expected light to behave the same way. If Earth is moving, then the speed of light should look slightly different depending on whether you measure it in the direction of Earth's motion or against it. But careful experiments didn't find that difference. Again and again, the measured speed of light in empty space appeared the same for observers moving steadily relative to one another. Physics faced a choice. You can keep the old idea of absolute space and absolute time and invent additional hidden machinery to explain why light stubbornly refuses to behave like a thrown ball. Or you can accept the simplest interpretation. The universe is telling you that your assumptions about space and time are slightly wrong. Modern physics chose the second option, and the result is one of the most elegant ideas ever discovered. The modern shift. Space and time are not separate, they are connected. The central insight is that if the speed of light is the same for all observers who are moving steadily, then space and time must adjust in their measurements to make that possible. This is not a mystical statement. It's a practical one. If two observers are moving relative to each other, they will not agree on certain measurements of distance and time. But they will agree on the laws of physics, and they will agree on the speed of light in empty space. To keep those agreements true, the universe reshuffles how space and time are divided up between observers. This means a few surprising things happen. Moving clocks do not match stationary clocks when compared carefully. Moving lengths do not match stationary lengths when compared carefully. And perhaps most strangely, two observers moving relative to each other can disagree about whether two distant events happened at the same time. That last point is the one that makes the mind reach for a handrail, because our brains are built for slow speeds on one planet. They are not built for a universe where now depends on motion. But the universe does not consult our comfort. It consults consistency. And this new consistency is called relativity, a gentle way to think about your time. Here's a calm way to approach it. In modern physics, the most meaningful time is not time for the whole universe. The most meaningful time is time along a journey. Imagine your life as a path through reality. Along that path, your heart beats, your thoughts shift, your body ages. That sequence is your time. It is the time measured by the clock you carry your physical processes. Someone else traveling differently through the universe, moving at a different speed, or sitting in a different gravitational environment, also has their own time along their path. When you meet and compare notes, you may find that the amount of time you experienced between two meetings is not exactly the same as the amount of time they experienced. That is not because one of you cheated. It is because time is not a single global drumbeat. It is a property of paths through the universe. This idea is surprisingly peaceful once it settles. It turns time from a strict dictator into a personal companion. Your time is real. Their time is real. The universe is simply more flexible than we assumed. Spacetime, the combined fabric behind space and time. To express this flexibility clearly, physics combines space and time into one structure: spacetime. Spacetime is not a poetic metaphor. It's a practical framework that helps explain why different observers measure different distances and different time intervals, yet still agree on the fundamental laws. In space-time, the basic things are events. An event is something happening at a location and at a moment. A flash of lightning, a heartbeat, a spacecraft passing a marker, a supernova exploding in a distant galaxy. Any happening Different observers can describe the same set of events with different coordinate choices, different ways of slicing reality into space and time. But beneath those descriptions, there is a deeper structure that remains consistent. That deeper structure controls what can influence what. It controls the limits of cause and effect. It tells you which events can send a signal to other events, and which are too far away, separated in such a way that no influence can travel between them fast enough. In everyday life, cause and effect feels obvious, but the deeper reason it works is that the universe has a built-in speed limit for information, and that speed limit is tied to space-time itself. So, space-time is not just space plus time. It is the rule book for the connectivity of reality. Gravity enters, and space-time becomes dynamic. So far, this picture describes motion when gravity can be neglected or treated lightly. But gravity is everywhere, and it turns space-time from a static framework into a living, responsive geometry. In the older view, gravity was a force. Masses attract each other across space. The Earth pulls the Moon. The Sun pulls the planets. You fall because the planet tugs you downward. That picture works very well in many situations. But modern physics found something even more elegant. Gravity can be understood as the shape of space-time. Mass and energy affect the geometry of space-time, and the geometry of space-time affects how objects move. Instead of thinking of gravity as an invisible rope pulling things together, you can think of it as a change in the straight lines of the universe. Objects travel along the most natural paths available to them, but those natural paths curve because space-time itself is curved. This is why planets orbit. It's not that they're constantly being yanked sideways in a mysterious way. It's that the space-time around the sun is shaped such that the most natural paths are curved loops. In this view, gravity is not just something that happens in space-time. Gravity is something space-time is doing. Time changes in gravity, and we can measure it. One of the clearest consequences of gravity as geometry is that time does not pass at the same rate everywhere. Closer to a massive object, time passes more slowly compared to farther away. This effect is tiny near Earth, but it is real, and it has been measured. This is not a distant, abstract prediction. It's part of modern technology. Satellite systems that help phones and navigation devices find your location rely on extremely precise timing signals. If engineers ignored the fact that clocks tick at different rates depending on speed and gravity, the system would drift and become inaccurate. So when you hear time dilation, it can sound like science fiction. But it is not speculative. It's part of the daily functioning of precision systems. The universe is quietly relativistic all the time. We just live in a regime where we don't feel it directly. And maybe that's comforting. Reality can be stranger than intuition, and still dependable enough to build on. Light bends. Not because it is heavy, but because space-time is shaped. In the older gravity as force picture, It's natural to ask, if gravity pulls things, does it pull light? In modern physics, the question becomes simpler. Light follows the natural straightest paths in space-time. But if space-time is curved by mass and energy, then the natural paths themselves are curved. So light appears to bend. This bending is observed in the sky. Massive objects like galaxies and clusters can act like lenses, warping the paths of light from objects behind them. Sometimes, the result is multiple images of the same distant galaxy, or elegant arcs of light stretched by gravity. This effect is one of the most beautiful confirmations that space and time are not passive scenery. The geometry is active. It shapes what you see. Space can expand, not just objects moving, but the stage itself stretching. When you zoom out from stars and galaxies to the universe as a whole, space-time offers another surprise. The universe is expanding. It's tempting to imagine this expansion as an explosion, with galaxies flying outward into emptiness. But that image has the wrong vibe. The more accurate idea is that the distances between far-apart regions increase over time because the geometry of space itself is changing. On large scales, galaxies are not necessarily racing through space like bullets. Instead, space is stretching, and galaxies are carried along with that stretching, like dots on a gently inflating surface. This expansion is not noticeable in your room, or in your body, or in the solar system, because local forces hold things together. Electromagnetism binds atoms. Gravity binds planets to stars and stars into galaxies. The expansion becomes important only across enormous intergalactic distances where those binding forces don't dominate. So space is not a rigid container. It can grow, it can evolve, it can have a history. And that means the universe is not just a collection of things in space and time. The universe is also the story of how space and time themselves behave. The arrow of time, why time feels like it moves forward. Even after you accept that time is not universal, there's another question that refuses to stay quiet. Why does time feel like it has a direction? You remember yesterday, not tomorrow. A glass can shatter, but it doesn't spontaneously reassemble into a perfect glass and leap back onto the table. Smoke spreads out. It doesn't gather itself neatly into a candle flame. In many fundamental physical laws, there is no strong preference for forward or backward time. The equations can often run either way, and yet our lived world is full of irreversible processes. The best scientific explanation connects this to entropy, which you can think of as a measure of how spread out energy and information are, and how many microscopic arrangements correspond to what you observe. A tidy room has fewer microscopic ways to be exactly that tidy room. A messy room has many more ways to be that level of mess. So, statistically, systems tend to move from fewer possibilities to more possibilities towards states that can happen in many more ways. That statistical drift gives the world its everyday sense of forward time. It's why heat flows from hot to cold. It's why cream mixes into coffee. It's why footprints appear in fresh snow and don't unappear. This does not mean time is an illusion. It means the direction you experience is connected to the universe's initial conditions and the way probability works in large systems. It's the universe, quietly, choosing what is typical. Now is not universal, but reality is still coherent. One of the biggest emotional hurdles in modern physics is the idea that simultaneity depends on motion that now is not the same for everyone across the cosmos. It can sound like the universe is fractured into separate personal realities, but that's not the message. The message is that reality is consistent, but your slicing of it into space and time depends on your motion. Different observers use different grids, and those grids don't line up perfectly. Yet the underlying cause and effect structure remains stable. In a sense, the universe is more like a shared landscape than a shared schedule. You and someone else can take different routes through the same terrain, and you may disagree about the best way to label the map, but you still meet at the same landmarks. The events are real. The relationships between them are real. The laws connecting them are real. Relativity doesn't remove structure. It reveals a deeper structure. Black holes, where space and time behave in extreme ways. If you want to see space-time's flexibility become dramatic, black holes are the natural place to look. A black hole forms when mass is concentrated so strongly that space-time becomes curved in a way that creates a boundary, a region from which light cannot escape to faraway observers. That boundary is called an event horizon. It is not a physical wall you could knock on. It is a feature of space-time geometry. It is a one-way limit for signals. What makes black holes so captivating is that they turn the usual roles of space and time upside down in certain ways. The future direction for anything inside the horizon points inward. Once you cross, you cannot choose a path that leads back out, because all paths that remain physically allowed lead deeper in. This is not about being pulled by a rope. It's about the way the geometry is arranged. Black holes also highlight gravitational time effects. From far away, processes near the horizon appear slowed, as if time is stretching. For an object falling in, its own experience can be calm crossing the horizon without a dramatic moment, at least for large black holes where tidal forces at the horizon are not extreme. Black holes are a reminder that space and time are not fixed. They can become so distorted that our everyday language struggles. Yet, the mathematics and the observations remain coherent. Space-time can ripple, gravitational waves. Another quietly astonishing discovery is that space-time can carry waves. When massive objects accelerate in certain asymmetric ways, like two black holes orbiting each other and merging, the disturbance in space-time can travel outward as a wave. These are gravitational waves. They are not sound waves traveling through space. They are not light waves. They are tiny oscillations in the geometry itself, minute, stretch, and squeeze patterns that move across the universe. Detecting them required extraordinary precision, because by the time they reach Earth, the effect is unbelievably small, and yet we have measured them. This is one of the most direct proofs that space-time is not just an abstract bookkeeping system. It behaves like a physical entity with its own dynamics. The universe is not only filled with things, the stage itself has motion. So, what is space? Scientifically, in simple terms, in the most grounded, measurement-based sense, space is the framework that allows distances, directions, and geometry to be defined between events and objects. But in modern physics, space is not just a container. Space can have curvature. Space can expand. Space can be influenced by mass and energy. Space can be part of a larger space-time structure that controls how signals move and how causes connect to effects. If you want a very plain sentence, space is the set of relationships that tell you how far apart things are, and those relationships can change depending on the universe's geometry. Space is not merely emptiness. It has properties, and those properties matter. So, what is time? Scientifically, in simple terms, time is the measure of change and the ordering of events recorded by clocks. In modern physics, the most meaningful time is the time measured along a particular journey, your own path through space-time. Time is not guaranteed to pass at the same rate everywhere. Motion affects time comparisons. Gravity affects time rates. And the directionality we feel, the forward flow, is closely connected to entropy and the way large systems evolve statistically. If you want a very plain sentence, time is what clocks measure, and clocks do not all agree when they move differently or sit in different gravitational conditions. Time is not a single cosmic soundtrack. It is more like many local melodies that harmonize according to consistent physical rules. The calm reconciliation why your everyday experience still works. After all of this, you might wonder why your life still feels normal. Why do you not feel your time dilating when you drive down the highway? Why does your living room not distort like a funhouse mirror because space-time is curved? Why does the universe not feel like an abstract geometry problem while you're trying to fall asleep? The answer is soothing. You live in a gentle part of reality. Human speeds are tiny compared to the speed of light. Earth's gravity is strong enough to keep you grounded, but weak compared to the extreme gravity near neutron stars and black holes. In this mild regime, classical intuition is an excellent approximation. Modern physics does not replace your experience. It refines it. It says your everyday space and time are accurate enough for daily life, the way a flat map is accurate enough to navigate a city. The deeper truth becomes important when you travel fast, measure precisely, or look across cosmic distances. So, your intuition is not wrong. It is local. And locality is one of the most honest themes in modern science. The universe as a story, written in space-time, If you step back and look at the big picture, the modern scientific view is almost quietly poetic. Everything that happens is an event. Events are arranged in space-time. Matter and energy shape the geometry. Geometry guides motion. Light carries information along allowed paths. The universe evolves, and with it, the geometry of space itself can expand and change. Even the most dramatic objects, black holes, exploding stars, colliding galaxies, are part of this same framework. They are not exceptions. They are expressions. And on the smallest, most personal scale, you are also an expression of it. You are a pattern of matter and energy moving through space-time, carrying your own time along your path, seeing the universe through signals that arrive at the speed light allows. That sounds grand, but it's also simple. You are here, now, in a lawful world. A gentle thought experiment. Distance is also a timing question. Here's a calm way to feel the connection between space and time without any mathematics. Imagine you want to measure how far away a wall is in a dark room. You could shine a flashlight, wait for the light to bounce back, and measure the time delay. If you know how fast light travels, you can infer the distance from the timing. This is not just a thought experiment. It's a deep hint. When the speed of light is fixed, measuring distance becomes tied to measuring time. So space and time are not independent bookkeeping categories. They are linked by how the universe allows information to move. In a sense, space-time is the bookkeeping system of information. And physics is, among other things, the study of what information can do. Why relativity feels strange but is deeply reasonable. Relativity often feels strange because it challenges assumptions we didn't even realize we had. We assume there is one shared now. We assume clocks are universal. We assume space is rigid. We assume motion is something you can define absolutely. But these assumptions were built by a brain optimized for a narrow band of speeds and sizes. The universe is not obligated to match that band. Relativity replaces absolute structures with relational structures, relationships between observers, signals, clocks, and events. And once you accept that reality is relational in this way, the strangeness becomes a kind of elegance. The universe stops feeling like it's playing tricks and starts feeling like it's enforcing a consistent set of rules. Rules that happen to be subtler than our instincts. What science knows confidently and what remains open, there's a peaceful honesty in modern physics. It is both incredibly successful and still unfinished. We understand how space-time behaves in an enormous range of situations. We can predict planetary orbits, the bending of light, the timing shifts in satellites, the behavior of objects near many gravitational fields. We can detect ripples in space-time from distant cosmic collisions. And yet, there are frontiers. At the smallest scales, quantum physics describes nature in probabilistic terms with extraordinary accuracy. At large scales, relativity describes space-time geometry with extraordinary accuracy. But combining these frameworks into one complete picture, especially in extreme places like the deep interior of black holes or the earliest moments of the universe, remains one of the great open projects of science. So if you ever feel a quiet awe about space and time, it's justified. The universe is knowable, but not exhausted. It invites curiosity. Even if you're listening to this only to drift to sleep, your mind is brushing against ideas that humanity has spent centuries uncovering. No pressure, just appreciation. A slow, simple summary you can rest with. Space is the structure that defines distances and geometry between things, and it can curve, stretch, and evolve. Time is the measure of change and the ordering of events along a journey, and it can pass at different rates depending on motion and gravity. Space-time is the unified framework that holds space and time together, setting the rules for how information travels and how cause connects to effect. And the reason these ideas matter is not because they are exotic, but because they are real. They have been tested. They power modern technology. They explain what we see in the sky. The universe is not just in space and time. The universe is space and time behaving, a quiet ending image for sleep. If you want to carry one calm image into rest, imagine the cosmos as a vast, dark ocean of geometry, smooth in some places, curved in others, gently expanding on the largest scales. Stars and planets move like boats following the natural currents. Light travels like whispers across long distances, arriving late but faithfully, carrying stories from far away. Your own life is a small, warm line traced through this immense structure, your personal sequence of moments, measured by the steady rhythms inside you. Your time is yours. Your place is yours. And the laws that hold everything together are steady, patient, and consistent. Space and time are not just background. They are the quiet architecture of reality. And as your breathing slows, you can let that architecture fade into a simple feeling. You are held gently inside a universe that makes sense even when it is wonderfully strange. Sweet dreams.